This video is brought to you by Skillshare. Get 3 months of learning for just 99 cents with the link below. Steel is the most important material to human society. It has been the skeleton of human industry for centuries, and the advent of the methods to mass produce it from iron ore was the impetus to transform human society from a mostly agricultural lifestyle to urban industrialization. It forms the backbone of our skyscrapers, it paves the way for our railways, it shapes the engines that powers our society, and the very tools that forge these objects are made from steel. We have spoken before about how the refining process of iron determines whether the resulting material will be iron or steel, and how the exact percentage of carbon present in the material has dramatic results on the final material properties, and how the production methods through time has taken steel from an expensive material reserved for swords, armour and toolmaking to one that is permeated into nearly every technology we use in our lives. But I failed to tell you why that simple addition of carbon has such a huge effect on the iron, turning it from a relatively weak material to one capable of launching an industrial revolution, which is what we're going to learn today. Much of our knowledge in crafting steel was passed down over the centuries from blacksmith to blacksmith, creating tools for their communities. So to learn more about this amazing material and how blacksmiths carefully tailor its material properties, I visited Alex Steele's workshop to create my own knife from scratch. We started our forging process with round stock 1055 steel with 0.55% carbon content, and placed it in the forge and gradually shaped it with a power hammer to a rectangular bar that could be more precisely shaped into the shape of our blade using a 3-pound hammer that my wee arms struggled to swing after an hour. Once we roughed out the shape, we began to grind and refine our blade, eventually producing our blade blank that would be later grinded to its final shape. But before that could happen, we needed to perform some metallurgy wizardry through the heat treatment process. To drive home how important this step is, we tested 4 samples of the same material at different stages of the heat treatment process. This was our sample before the heat treatment process, which you will quickly see was the weakest of the bunch. This is the normalized sample, which was ductile with a low yield stress. It took several hammer blows, which it absorbed through plastic deformation, not ideal characteristics for a sword or knife. Next we tested our quench hardened sample, which is stupid and dangerous and should not be tried at home. This fractured explosively and tore a hole through Alex's reflector. Finally we tested the tempered material, which absorbed every hammer blow with minimal plastic deformation and only broke when we cut a notch into the material to create a stress concentration point. This material is tough, capable of absorbing energy without deforming permanently, and hard, allowing it to resist damage to the cutting edge. It is the ideal material for a blade. If any of these terms confuse you, I created a video called Material Properties 101 that you can check out to get a better understanding of material property terminology. So how can the same steel alloy change so radically by simply applying heat? Well, this is the magic of the iron-carbon alloy. We can carefully control how the internal metallic crystal structure forms with heating and cooling cycles. First, let's see how adding carbon to the iron affects the crystalline structure. With no carbon present, pure iron forms a crystal structure called body-centered cubic with an iron atom at each of the 8 corners and another in the center. Each crystal structure has a direction it most easily wants to deform, called a slip plane. For body-centered cubic, the slip plane occurs along this plane. Metals with body-centered cubic crystals like iron and tungsten tend to be harder and less malleable than metals with face-centered cubic crystals like aluminium, lead and gold. When a metal is cooling, these crystals grow from individual nucleation points and form grains where each grain has the same orientation of slip plane, but neighbouring grains may not have the same slip plane. Let's think about this 2-dimensionally. When a force is applied, the grain wants to slip in a particular direction and passes the force onto the next grain in that direction too. But this grain's slip plane is at a different angle, so that force needs to be greater in order to cause deformation. It's like trying to push a train down a railway track by pushing on its side. It's not going to go anywhere easily. So smaller and more numerous grains results in a stronger material. Pure iron tends to always have the same crystal structure as it cools, and its crystal structure doesn't change meaningfully with heat treatment. This is where alloying with carbon comes in. To explore this, let's look at our phase diagram for carbon steel. On this diagram, we have our carbon content percentage on the x-axis and the temperature of the metal on the y-axis. This tells us the crystalline structure of the metal at various temperatures and carbon contents. On the left-hand side, we have pure iron, which, as we explained earlier, forms only one crystal structure called ferrite. As we move across the diagram to the right-hand side, less and less of the crystal structure forms ferrite, and more forms an iron carbide alloy, commonly called cementite. Now if we move up in temperature, we start to see these lines that represent transitional temperatures, where the crystal structures of the steel begin to transform into a new crystal structure called austenite. Moving further up again, we see these lines representing the transition of the material to a liquid state. Austenite's primary difference to ferrite is that it forms that face-centered cubic crystal structure that we saw earlier, while ferrite is body-centered cubic. And while this packing pattern is denser than body-centered cubic, it does open up spaces in the crystal structure that interstitial carbon atoms, which are smaller than iron, can snugly fit, allowing austenite to have a higher solubility to carbon over ferrite. Using all this information, let's take our 1055 steel with 0.55% carbon content and see how it transforms from the start of our heat treatment cycle to the end. The first step is called normalization. Normalization's primary function is to relieve internal stresses and strains that form during the forging process and return the material to its original crystal structure before forging began. It's effectively a reset button for the steel and creates a nice even grain size and distribution, increasing its strength. Here we place the knife inside a steel tube to prevent the metal from receiving heat directly from the flame, but instead a more even radiative heat from the tube. Once it reaches this transition temperature, we let it soak to give the crystal structure time to settle. The next step in normalization is to allow the steel to slowly air cool. What happens now depends on the carbon content. If we take a 0.8% carbon steel, no, hang on, we're definitely going to need a bigger graph for this. Okay, if we take a 0.8% carbon steel and cool it through the transitional temperature, the austenite and the interstitial carbon will slowly transform to a mixture of ferrite and cementite, which takes this laminar structure called pearlite. Pearlite only forms at a 0.8% carbon solution. Now if we take a 0.2% steel and slowly cool it to its first transitional temperature here, where ferrite first begins to form. Ferrite is pure iron, so as it forms the carbon percentage begins to rise. This will continue to happen until the remaining austenite has a carbon percentage of 0.8% and will then form pearlite from this point on. This forms a crystal structure dominated by ferrite, showing here as a lighter colour, surrounded by the darker pearlite. Comparing these microstructures to another two, we can see the effect carbon has on the microstructure. Here we have pure iron with 100% ferrite, showing us the light colour. You can even see the grain boundaries. This is 0.5% carbon steel, similar to ours, where a very small amount of ferrite formed before reaching the point of pearlite formation, and this is 0.8% carbon steel, where the entire structure is pearlite, with our previous example showing pearlite under 500 times magnification, where you can readily see that laminar structure. How pearlite strengthens steel is not well understood. It has little effect on the steel's stiffness, but increasing the pearlite content has a dramatic effect on the material's yield point, making it much more capable of absorbing energy without permanently deforming. But we can increase the material's stiffness and hardness with our next step. If we heat the metal back up to form austenite once again, but this time instead of letting it cool slowly, we rapidly cool it in oil while casually burning your arm hair off and barely flinching, the carbon atoms that spread out throughout the hot austenite structure cannot diffuse out of the crystal lattice to form cementite, and instead get stuck in solution, creating a new crystal structure called martensite. This crystal structure has a huge amount of internal stretching, in part because the carbon trapped within the crystal structure causes the crystal lattice to deform, but also because during the rapid cooling, the surface cooled much faster than the internal material. This causes internal tension in the material. These internal strains make it harder for additional deformation to occur, but this does not make the material stronger. It simply means that it will not stretch and bend before breaking. And when it finally does fracture, all of this internal tension is suddenly released in an explosive expansion. If you've watched Smarter Everyday's video on the St. Rupert's drop, you'll have seen this principle demonstrated in incredible slow motion. This material property is called hardness, and we want our cutting edge to be hard to resist damage when cutting. But we do not want our entire blade to be hard, as it will not be able to absorb a lot of energy. It needs to be able to dissipate some of that energy through heat and deformation. This is where the final step of the process comes in, called tempering. Tempering raises the temperature enough to allow the carbon trapped in solution to escape. We just use an oven set at 200 degrees. The carbon then coalesces to form cementite once again, but instead of forming pearlite like before, it gathers in globules surrounded by ferrite. Tempering also relieves some of that internal tension caused by the rapid cooling. This reduces the hardness but increases toughness. This produces a material that has the perfect balance of characteristics between the normalized material and the hardened material. It is ductile enough to absorb hammer blows without shattering, but strong enough to not permanently deform, and with enough hardness to ensure it doesn't gather damage on the cutting edge. This process gave our steel the perfect material properties, and a lot of that is thanks to the quality of the steel we started off with. Learning these skills with Alec was a lot of fun, and I highly recommend you check out his channel. His incredible attitude to work really inspired me to start learning some new hands-on skills this year, and I'm hoping to start that off by learning how to program and create robotics with an Arduino. This course I found on Skillshare is the perfect jumping off point for anyone looking to learn the same skills. Skillshare is home to thousands of other classes in graphic design, animation, web development, music, photography, video game design, and more. These days you can teach yourself pretty much any skill online, and Skillshare is a fantastic place to do it. With professional and understandable classes that follow a clear learning curve, you can dive in and start learning how to do the work you love. A premium membership begins around $10 a month for unlimited access to all courses, but you can get your first 3 months for just 99 cents if you sign up with this link. This offer was supposed to be only valid until the end of January, but I talked to Skillshare and I was able to get this extended free until February 15th. In those 3 months, you could easily learn the skills you need to start a new hobby or business. So ask yourself right now, what skill have you been putting off learning? What project have you been dreaming of completing but you aren't sure if you have the skills to do it? Why not start right now and sign up to Skillshare using the link below? You've nothing to lose and a valuable life skill to gain. As usual, thanks for watching, and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Twitter, Facebook and Instagram pages are below.